All right, so let's do two examples of an analysis of variance with all four steps of the hypothesis test, calculation for effect size, and the Tukey post hoc analysis to see which groups are significantly different. So in this first scenario, research wants to study the effectiveness of morphine versus fentanyl on pain intensity among chronic pain patients. So he randomly selects 15 chronic pain patients from a local rehabilitation therapy clinic and invites them to participate in a study. And he randomly assigns 5 participants to 3 different treatment conditions. So 5 of his participants are in the morphine group, 5 are in the fentanyl group, and 5 are in a control group where they just get a sugar pill instead of pain medication. All of these people are asked to use only the medication that they were assigned in their study for the next 3 days. And then after the 3 days, the participants provide a rating of their pain relief on a scale from 0 to 10. So in this case, the dependent variable would be pain, right? Pain relief. So if you have a difficulty keeping straight, what's my independent variable, what's my dependent variable? The dependent variable is what is measured. So you can ask yourself, what do these scores represent? Well, these scores represent pain relief on a scale from 0 to 10. Pain relief is what we are measuring. Pain relief is our dependent variable. What is the independent variable? So the independent variable is what we're actually manipulating. Or if it's a quasi-independent variable and it's something that's pre-existing, it's just generally the basis of our groups. So the basis of our different groups would be the different drug, the different pain relief drug. And how many levels do we have? We have 1, 2, 3 levels. There's 3 different groups, 3 different conditions, 3 different treatment groups, because we have 3 different levels of the independent variable, 3 different types of drug. Whereas, one's a control group, it's just a sugar pill. Then we want to know, do the results suggest there's a significant alpha level 0.01 difference in pain relief among the 3 groups? And if so, what's the size of the effect and which groups are significantly different? So if you're asked for which groups are significantly different, or is there a significant difference in pain relief based on the drug, you need to do all 4 steps of a hypothesis test. If you're asked to calculate effect size for ANOVA, you're finding eta squared. If you're asked which groups are significantly different, you need to do the Tukey's post hoc analysis. Because remember, ANOVA just tells you there's a difference somewhere. We don't know where those differences lie, so if you want to figure out which groups are significantly different, it's time to do a Tukey's post hoc analysis. All right, so let's go ahead and start with step 3, because I usually do that, get the calculations out of the way so that we have our degrees of freedom for step 2. All right, so let's calculate our test statistic, step 3. So the first thing that I'm going to find, and first actually I'm going to go ahead and draw my source table down here, just to remember that I need to put all of my values into it, and so that I can keep everything organized. So I have my source, and source just represents the source of variability. So we have the between groups variability, the differences due to error and the independent variable. We have our within groups variability, and then the total variability. Then we have our sum of squares, degrees of freedom, our variance, or our mean squares, and then we finish with the F statistic. All right, so as I find my values, I'm going to place them into this table. So remember, the first thing that we want to figure out is the sum of squares within and the sum of squares total, so we can take the difference to find the sum of squares between. So let's go ahead and start with the sum of squares within. So SS within. Now, when the sum of squares for each group is given to you, it's pretty darn simple to figure out the sum of squares within. You just add all the differences within the groups. So think about it conceptually. The sum of squares within just tells you the differences within the groups, and the sum of squares tells you the differences within each group. So you just add those differences within each group to get the sum of squares within. So we have 12 plus 20 plus 14. Again, those are given to you right here. So 12 plus 20 plus 14 gives me 46. So right here, sum of squares within, I'm just going to write 46. Now let's write down the formula for sum of squares total. So sum of squares total. So that formula is a little more difficult. That one is the sum of x squared minus the grand total squared divided by the sample size for the entire study. So I need to find what is g and what is my sum of x squared and what is my uppercase N here. So the way that I can find the sum of x squared is I can literally square each score and add it together. So I'm just going to start doing a little bit of x squaring over here. So 0 times 0 is 0, 4 times 4 is 16, 0 times 0 is 0, 1 times 1 is 1, 0 times 0 is 0, 6 times 6 is 36, 8 times 8 is, I believe it's, I don't know that one in my head, 64. All right, had to check. I thought it was 64. There we go. 5 times 5 is 25, 4 times 4 is 16, 2 times 2 is 4. 6 times 6 is 36, 5 times 5 is 25, 9 times 9 is 81, 4 times 4 is 16, and 6 times 6 is 36. Add all of those values together, and you end up with 356. Then we need to find what G is. Well, remember, G stands for the grand total. So if we add all the scores together, and I'm going to go ahead and color code this. So sum of x squared, that's all these guys added together. And then my grand total, you just add all these together. So you take 0 plus 4 plus 0 plus 1 plus 0 plus 6 plus 8, all those scores added together, and you end up with a value of 60. We're going to have to square that at some point. And then we divide by the sample size for the entire study. So we have 5 different people in 3 groups. 5 times 3 is 15. Now, if we wanted to fill in all those values that I mentioned on the statistical notation page, like t and lowercase n, we could do that. So we could say, all right, T1, T2, and T3. Remember, that's the sum of x for each group. So if we take 4 plus 1, we get 5. 6 plus 8 plus 5 plus 4 plus 2 gives you 25. 6 plus 5 plus 9 plus 4 plus 6 gives you 30. So just looking at this, I feel like morphine is resulting in more pain relief, but I need to do all my significance testing to figure out if we would think that would happen in the population. Then my sample size for each group. So each group has 5 people in it. Then I could also figure out my means for each group because I know I'm going to need that eventually when I'm doing my Tukey's post hoc analysis. So 5 divided by 5, right? The sum of x, or t in this case, divided by n is 1. 25 divided by 5, the sum of x in this case divided by 5 is 5. And 30 divided by 5, 30 is the sum of x, or t in this case, divided by the sample size of 5, gives me 6. So I've just got all my information filled in right there for you. Alright, so let's go ahead and finish our calculations for sum of squares total. So I'm going to do one step at a time. I need to solve for my exponent first. So this becomes 356 minus, so 60 times 60 gives us 3,600. And we're going to divide that by 15. Then this becomes 356 minus, well, 3,600 divided by 15 gives me 240. And I end up with 116. So my sum of squares total, 116. Now, just for kicks on this first example, I'll show you both ways to find the sum of squares between. The not so fun way and then the easy way. At this point, remember, my sum of squares between plus my sum of squares within is going to equal my sum of squares total. So to find sum of squares within or between, I can simply take sum of squares total and subtract sum of squares within. And so I could do sum of squares between is equal to the sum of squares total minus the sum of squares within. And 116 minus 46 gives me 70. Put it right there in my table. But you know what? I'll show you how to confirm this using the formula for sum of squares between. So sum of squares between. So that was the sum of t squared divided by n minus g squared divided by uppercase n. So remember in the conceptual lecture I said that for this formula you're going to have however many groups you have, you're going to have that many of these, right? You're summing all the totals for each group divided by all the sample sizes for each group. So the total for group 1 would be 5. We're going to square that and divide by the sample size, which is 5, plus for group 2, the total was 25, and the sample size was 5. For group 3, the total, the sum of x, was 30. Sample size was 5. So we're going to do all of those and then subtract by the grand total, which we already found, right? And I'll just write it here again. But we already found it for sum of squares total, and it was equal to 60, which is the same as 5 plus 25 plus 30, right? Because these are all the totals for each group. Add them together, you get the total for the entire study. So G, the grand total, is 60. Square that. Divide by the sample size for the entire study, which is the same as saying little n plus little n plus little n, right? 5 plus 5 plus 5. There's 15 people in the entire study. So now we need to solve for the exponents first. So this becomes 25 divided by 5 plus, well, 25 squared gives me 625. 30 squared is 900. And then 60 squared is 3600. Now let's go ahead and solve for my division, right? Let's turn these fractions into regular old numbers. So 25 divided by 5 gives us 5. 625 divided by 5 gives me 125. 900 divided by 5 gives me 180. 3600 divided by 15 gives me 240. So we solve for the parentheses first. So 5 plus 125 plus 180 gives me 310 minus 240. And I get a sum of squares between of 70. This formula is tons of fun, but if you're not a mathy person like I am, you probably want to opt for the simpler version. Find sum of squares total, find sum of squares within, take total minus within, you've got sum of squares between. I just wanted to show you that it gives you the same answer either way. On the next example, I'm not even going to go there. I'm just going to go with the easy version. Okay, now our next step is we need to find our degrees of freedom between within and total. Now, we don't really do anything with total when it comes to calculating f. I just like to find it to confirm that these are correct. My sum of squares between and within and my degrees of freedom between and within. All right, so my degrees of freedom between. And that is equal to k minus 1. So what is k in this example? Well, how many levels do we have? 3. We've got control, fentanyl, and morphine. So 3 minus 1 is 2. Slap that into our table. Then degrees of freedom within is equal to n minus k, uppercase n minus k. So there's 15 people in the entire study minus 3 groups. You get 12 degrees of freedom within. Then my degrees of freedom total, at this point it better equal 14, right? Because we think 2 plus 12 is 14. Well, let's just double check. It's equal to the sample size for the entire study minus 1. 15 minus 1 is in fact 14. Oh boy, I'm feeling good. Then I just take this divided by this to get this, and this divided by this to get that. So my mean squared between is equal to my sum of squares between divided by my degrees of freedom between. So I have 70 divided by 2 is 35. So just stick that right there. Then my mean squared within is equal to my sum of squares within divided by degrees of freedom within. So 46 divided by 12, and I end up with 3.833. So at this point, I'm feeling pretty good about what F's going to look like, because remember, this includes the variance in my dependent variable, pain, that's due to my independent variable and error. This is the variance in my dependent variable, pain, just due to error. This is quite larger than this, so I'm feeling pretty good that my independent variable, the pain drug, is having an effect on my dependent variable. That the differences are probably due to the different drugs and not just due to random differences within each group. Now let's go ahead and calculate F. And I'm going to put F in blue because it's super important. Alright, F is equal to the mean squared between divided by the mean squared within. So 35 divided by 3.833. So in other words, to find your values, you take this divided by this to get this divided by this to get this, and this divided by this to get F. And 35 divided by 3.833 gives me 9.131. So the differences in my dependent variable due to my independent variable are 9.131 times larger than the differences due to chance. 9.131. And that's your final value. That's your F observed, your test statistic for step 3. Alrighty. Now let's go ahead and jump back to our step 1 and our step 2 and then our step 4. Okay, so step 1, stating our hypothesis. So our alternative is that at least one mu is significantly different. All right. Then our null, in this case, we have 3 groups, so we'd have mu1 is equal to mu2 is equal to mu3. Done. All right. Step 2Z. Find your F crit. So to find F crit, we need to know the alpha level. In this case, it's 0.01. We need to know the degrees of freedom numerator, which is the same as saying degrees of freedom between. We also need to know the degrees of freedom denominator. Or in other words, the degrees of freedom within. Now the reason it says numerator and denominator in the F table and it doesn't say between and within is because, as you'll see when we get to regression, there's different types of tests that use F, and it's not always looking at between versus within. So it keeps it as numerator versus denominator. Alright, so let's go ahead and go back and see. So our degrees of freedom between is 2. Our degrees of freedom within is 12. So 2 and 12. Now we're ready to go to our F table to find our critical value. So we go to our statistical tables. We're done with the unit normal table. We are done with the t-distribution. Now don't look at F max. Don't even worry about that. That's to figure out if you have homogeneity of variance for the t-test for independent samples. We want just the plain old F distribution. So you'll see that positively skewed distribution, right? Under the null, most of F values are 1, meaning there's no difference due to the independent variable. Degrees of freedom numerator, or degrees of freedom between, was 2. Degrees of freedom denominator, or the degrees of freedom within, was 12. So where do 2 and 12 meet? Right here. 3.88 would be the alpha, or the critical value if our alpha level is 0.05. Our alpha level is 0.01, so we're going to go with 6.93. And because this is F, we don't have to worry, is this a positive or a negative value? It's always going to be positive. So 6.93 is our critical value. And I'm going to go ahead and draw that distribution, just because I like to draw my distributions. So we've got our frequencies, and then we've got our F statistics down here. Remember our positively skewed distribution. 1 is right here, 0 is right here, and 6.93 is roughly here. So just like before, if our obtained test statistic from step 3 falls outside of the critical value in the critical region, we can reject the null hypothesis. If not, we are failures, and we fail to reject the null hypothesis. So if we go back and we look at our test statistic, 9.131, it's like here-ish, right? So we can rejoice in rejecting the null hypothesis and step 4. So remember, step 3, we found that our F observed was equal to, what was it again? 9.131. Step 4, reject the null. And now we want to state our conclusion. And be careful when you state your conclusion. You want to include the word significant. You want to include your dependent variable, your independent variable, and you want to indicate if results were significant or not. So, and I usually start with results suggest, just to indicate the fact that we know this isn't the end-all be-all for research. Studies are cumulative. They build upon each other. There's no one single study that really proves anything for certain. So results suggest that there is a significant difference, right? That word significant is important. Significant difference in pain relief among the 3 pain medication conditions. You could also say there's a significant difference in pain relief based on which drug was taken, if you want to be less specific. So I have my dependent variable, I have my independent variable, and I have the word significant. Now, let's say that we got an F value that did not fall in the critical region. Then we would say, results suggest there is not a significant difference in pain relief among the 3 pain medication conditions, and we'd be done, because we don't really care about effect size or which groups are significantly different if we fail to reject the null. But we did reject the null, so it's time to figure out our effect size. Or, here's my sad little attempt at eta. Eta squared. And remember, the formula for eta squared is the sum of squares between divided by the sum of squares total. So you're basically saying the variance that's due to the independent variable and error divided by the variance for the entire study. Or, sorry, the variability. Variance doesn't come into play until we do mean squares, when we divide that by degrees of freedom. And if we go back to our source tables are beautiful. We can find our values quite quickly. We're saying 70 divided by 116. And we have 0.603. And this would be a very large effect. It exceeds 0.25. So if you were asked to interpret this in plain English, remember, eta squared tells you the proportion of the variability in your dependent variable that can be accounted for by your independent variable. So if you think about this, like let's go ahead and multiply this by 100 to turn it into a percent. We could say 60.3% of the variance, which is really just a fancy word for differences, in pain relief is accounted for or predicted by or due to the medicine condition participants were in, or the medication that they received. Now, I like r squared because you can think about it as a pie. This pie represents 100% of the differences in pain relief, right? These are all the little differences in pain relief. And we know that 60.3% of those differences, or roughly, oh gosh, I'm not good at pies, but like this much of the differences is accounted for by which pain medication they received. The rest of this is really due to anything else. So maybe their age, maybe the type of pain that they're experiencing, maybe how in shape they are, how fit they are, how well they take care of themselves, anything else that's going to result in differences in pain relief. Now, one thing that's beyond the scope of this class that I can't help but mention, if you start looking at more independent variables, you're going to start to see a shrink in this, even if you're still looking at the same drugs among the same people, because once you start to look at other pieces that predict that variability, there may be some overlap with, for instance, drugs and something else that you could measure as an independent variable. And so you may see that shrink a little bit. So this may overestimate the effect of drugs because we only looked at drugs. We didn't look at any other independent variables that could have an impact on pain relief. Just kind of a methodological addition to this. All right, so now we found the effect size. It's huge. We're feeling good about this. Now it's like, okay, so what, right? We know there's a difference somewhere, but we don't really know where those differences lie. And practically speaking, if I was using this study to make some sort of decisions, I really wouldn't be able to tell anybody which drug that they should use for their pain because I don't know which groups are significantly different. So this calls for a Tukey post hoc analysis. And remember the formula for that, and I'm just going to abbreviate it, HSD, right? Tukey's honestly significant difference is equal to Q times the square root of the mean squares within divided by the sample size for each group. And remember, this is going to give me the mean difference necessary between two groups to conclude that those two groups are significantly different. So first, I need to find Q in the table. So let's go to our table. And remember, our degrees of freedom error, I'll go ahead and write this here. Degrees of freedom error is equal to the degrees of freedom within, which was equal to 12 from our source table. All right, table time. So you want to go to the table that follows the F table. It's the studentized range statistic. Q, right? There's our Q. And we're looking for degrees of freedom error of 12 with K equals 3 because we had 3 groups. And we're using alpha level 0.01, so we're going to go with the bold value. which lands us right here on 5.05. So Q is equal to 5.05. That's not HSD, that's just Q, 5.05. Now we need to multiply that by the mean squared within, which is equal to, see, source tables are beautiful. Find our value, 3.833. Divided by the sample size for each group, which was 5. So this becomes 5.05, I'm doing one step at a time, times the square root of 3.833 divided by 5 gives me 0.766. And so this becomes 5.05. Square root of 0.766 is 0.875. And you end up with the Tukey's HSD of 4.419. So what this tells us is that we have to have a mean difference of at least 4.419 points between any two groups to conclude that those two groups are significantly different. So let's go ahead and look at our means that we calculated earlier. So group 1 had a mean of 1, group 2 had a mean of 5, and group 3 had a mean of 6. So I'm going to go ahead and rewrite those. So the mean for the control group was equal to 1, the mean for the fentanyl group was equal to 5, and the mean for the morphine group was equal to 6. So now we need to figure out all of the possible pairwise comparisons to see what the mean differences are to then compare that to Tukey's HSD, which I'm going to color code in blue. Alrighty. So we need to take the mean for the control group minus the mean for the fentanyl group. We need to take the mean for the control group minus the mean for the morphine group. And then that only leaves one comparison, right? The mean for the fentanyl group compared to the mean for the morphine group. And when we're doing this, we really only care about absolute differences. It doesn't matter if they're negative or positive. We just care about the absolute differences. And if that's greater than Tukey's HSD. So the mean for the control group is 1, the mean for the fentanyl group is 5, and we're looking at a difference of 4. The mean for the control group is 1, the mean for the morphine group is 6, absolute difference of 5. And the mean for the fentanyl group is 5, the mean for the morphine group is 6, absolute difference of 1. Well, this is less than 4.419. So this is not a significant difference with an alpha level of 0.01. Then this difference is greater than 4.419. So we conclude that this is a significant difference with an alpha level of 0.01. Sweet. There's our group that's significantly different, because check this out. 1 is definitely less than 4.419. Not a significant difference with an alpha level of 0.01. Now, if you were asked to describe this in plain English, you could look at this and you could say, okay, there's no difference between no drug at all and fentanyl. And there's no difference between fentanyl and morphine. So really, the only difference exists between the control group and morphine. So, in plain English, we could say, in the population, right? Because that's what these results are supposed to extrapolate to. In the population, morphine is expected to be more effective for pain relief than no drug at all. So is expected to be more effective for pain relief. Then no drug at all. So now we have an actionable finding, right? Before we just said, there's some difference. The ANOVA was significant. But now we know we need to give people morphine compared to fentanyl and compared to a sugar pill. So go ahead and pause this video and attempt the next problem in your slides, where we're looking at the relative effectiveness of different types of punishment for traffic violations. Pause this video, give it a try on your own before you watch the answers. All right, so in this example problem, law enforcement officials want to know what is the most effective way to stop repeat traffic violations. So they take 15 traffic offenders and they randomly assign 5 to each group, and there's 3 different groups. One group gets 2 weeks community service, another group gets a $75 fine, and another group gets 2 weeks of driver's education. Then they measure the number of traffic violations in the following year. So just like before, what are we measuring? What do these numbers represent? They represent the number of traffic violations in the following year. Traffic violations is our dependent variable. What are these different groups based on? Different types of programs. Programs is our independent variable, and we have 3 levels of our independent variable because we have 3 different types of programs in our study. Okay. So we want to determine whether there are significant differences in traffic violations depending on which program people received with an alpha level of 0.05. If significant differences exist, we're going to look at the eta squared, the effect size, and determine which groups are significantly different from each other using Tukey's HSD. So I'm going to go ahead and just fill in all my little, my values under my table before I start doing my calculations for step 3. So I've got my sum of squares given to me. How generous. That's the only thing that's really painful to figure out. And now let's see. What is, because we know we need to figure out sum of x squared at some point. I need to know what my g is at some point, my grand total. I need to know what my sample size is for my entire study, sample size per group. I also would like to know what my t is for each group. Just for kicks. I'm not going to use that crazy formula for sum of squares between, but just to give you practice finding these things. And we just call this group 1, group 2, and group 3, just because writing T community service, T $75 fine, and T driver's education is a little bit tedious. And let's go ahead and find our means for each group, because we know if we find significant results, we're going to need to use those for Tukey's HSD. So if I add 1 plus 3 plus 1, I get 5 for T1. If I add 4 plus 3 plus 6 plus 3 plus 4, I get 20, the sum of x for group 2, or T for group 2. And if I add 1 plus 2 plus 2, I end up with 5 for the sum of x, or T for group 3. I know that I have 5 people in each group. So 5 divided by 5 gives me 1. 20 divided by 5 gives me 4. 5 divided by 5 gives me 1. Then I need to find my sum of x squared. So I just square each one of these. So 0, 1, 9, 1, 0, 16, 9, 36, 9, 16, 1, 4, and 4, and zeros. Add those together and you get 106 for sum of x squared. Then g, you can just add your t's together, right? You could add all the scores together, or just add your t's. 5 plus 20 plus 5 gives me 30 for my grand total. And then I've got 5 individuals in 3 different groups, 15 total sample size. So let's go ahead and jump right to step 3. Let's fill in our source table and then use that information to figure out what is everything else that we're looking at as far as calculations go. So I'm just going to write this down here. We've got our source. We've got between, differences due to the independent variable and error. We've got within, just the differences due to error. And then we've got total. We've got our sum of squares, the overall differences, the degrees of freedom, the mean squared, the average differences or the variance, and then our F statistic. Okay, let's start off with sum of squares total. Just start from the bottom and work our way up. I always find sum of squares total and within first, take the difference for sum of squares between. So remember this formula, sum of x squared minus g squared divided by n. Sum of x squared is 106, g is 30, and uppercase N is 15. One step at a time, let's go ahead and say, just copy everything except for what we're solving, right? So 106 minus 30 squared is 900 divided by 15. This becomes 106 minus 60, which gives you 46 for your sum of squares total. Boom, there it is. Then sum of squares within. Simply add the sum of squares for each group. So we have 6 plus 4. So that gives us 16. So plop that right in there for your sum of squares within. Then sum of squares between. Just take the sum of squares total minus the sum of squares within, and you have 46 minus 16, and you get 30. Now, if you want to test that calculation using the extended version of the formula, be my guest. Then we've got degrees of freedom between, which is equal to k minus 1. And what is k in this example? Well, k is equal to 3. We have 3 groups. 3 minus 1 is 2. And then our degrees of freedom within is equal to n minus k. And n is 15 minus 3, 12. So we've got 2 and 12. And then our degrees of freedom total is equal to n minus 1. 15 minus 1 is 14. This was just like the previous example because we had the same sample size and the same number of levels. Okay, now let's figure out our mean squared between. You simply take the sum of squares between, divide by the degrees of freedom between. Just like variance, right? Because this is the variance. 30 divided by 2 is 15. Bam! There we go. Mean squared within. The sum of squares within. Divided by the degrees of freedom within. We have 16 divided by 12. And we end up with 1.333. Just plug that right in there. Then F, make it in blue so it stands out. It's so important. We have the variance due to the independent variable and error, or the mean squared between, divided by the variance just due to error, or the mean squared within. 15 divided by 1.333 gives you an F statistic of 11.253. Huge, right? 11.253. So the differences due to the independent variable are 11.253 times larger than the differences just due to random differences within groups. You can kind of think of it that way to keep it simple. All right, that's step 3. We need to go back and do step 1, 2, and 4. Step 1, let's state our hypotheses. I'll start with our null this time. That's just saying there's no significant difference between these 3 groups. So this is saying that if we fail to reject the null, then we don't think that there's any difference in traffic violations based on which type of program people in the population would receive. This one, at least one mu is significantly different. All right. Step 2, we need to find our F critical using an alpha level of 0.05, a degrees of freedom numerator, or in other words, the degrees of freedom between of 2, degrees of freedom denominator, or in other words, the degrees of freedom within of 12. Let's pop over to our table here. So we look at our F distribution. Degrees of freedom numerator, or degrees of freedom between, is 2. Degrees of freedom denominator, or degrees of freedom within, is 12. And we land right here. This time we're using an alpha level of 0.05, so we go with the light face value. 3.88 is our critical value. And again, there's no negatives with F values, so we don't have to worry about is it positive or negative. And if we draw our F distribution, 3.88, as long as our F that we calculated in step 3 falls out here, we can reject the null and know that at least one group has a significantly different level of the dependent variable. So step 3, remember we found our F statistic, or our F observed, to be 11.253. And that is like out here in the ether, right? There's just no way that it's due to chance. It's due to the independent variable. We're pretty certain of that. So for step 4, we make our decision. We reject the null. And our conclusion would be, remember, we're reflecting the fact that we just know there's at least a significant difference somewhere. So we would say, results suggest that there is a significant difference in traffic citations depending on which program participants were assigned to. You guys hear my squeaky pen on my screen? Hope it's not too annoying. Okay, so results suggest there's a significant difference in traffic citations depending on which program people were assigned to. So based on this, we would expect that if we initiated these 3 different programs in the population, we would see a difference across traffic violations there as well. But what we do not know is which group or which type of program is the most effective, right? We have to figure out Tukey's post hoc analysis to do that. We also do not know the effect size, so we don't know the so what piece of this. Is there a substantial difference? Yeah, it could be significant. We could know that there's a difference through the independent variable, but we don't really know how substantial that difference is until we calculate effect size. So let's go ahead and figure out eta squared, our measure of effect size, which is equal to the sum of squares between divided by the sum of squares total. So our sum of squares between is 30, right? And our sum of squares total is 46. So our r squared is 0.652. So we can say, if we multiply this by 100, turn it into a percent, because it's a proportion right now, 65.2% of the variance, or of the differences in traffic citations, right? That's what we're measuring, our dependent variable, is predicted by which program people were in, or is due to the program people were in, or is accounted for by which program people were in. I'm going to call them traffic offenders now instead of just people. So if we drew our delicious pie of differences in traffic citations, yummy, 65.2% of all those differences can be accounted for by the program. And then the remainder of those differences are due to something else other than our independent variable. All right. Now let's figure out which of these groups are significantly different. So we need to find Tukey's HSD, the honestly significant difference. And don't you be calling it turkey either. It's Tukey. All right. So we have our Q multiplied by the square root of the mean squares within divided by the sample size for one group, for each group. And real quick, I'm just going to jot down my means that I found earlier. So remember, let's see, the mean for group 1 was 1, the mean for group 2 was 4, and the mean for group 3 was 1. That's easy enough. So 1, 4, and 1. Now, to me right now, it's pretty obvious which groups are significantly different, but I'm going to go through and find Tukey anyway, just to give you guys some practice and to show you that you always need to do this. All right, so we need to find Q based on an alpha level of 0.05, 3 groups, and degrees of freedom error, or in other words, degrees of freedom within, equal to 12. All right, so let's hit up that table. Go down to Q. Q. 3 groups, degrees of freedom error of 12, and now we are using an alpha level of 0.05. So Q is 3.77. Remember, 0.01 bold, 0.05 light face type. And it even says that up here, if you forget. So 3.77 is Q. And then our mean squared within was equal to 1.333 divided by 5, the sample size for each group. So this becomes 3.77 times the square root. So 1.333 divided by 5 is 0.266. Take the square root of 0.266 and you end up with 0.516. And 3.77 times 0.516 gives you 1.945. So that is the mean difference necessary between two groups to conclude that those two groups are in fact significantly different. All right, so let's go ahead and find all of our mean differences. So the mean for community service minus the mean for the $75 fine. We'll need to take the mean for community service, subtract the mean for driver's education, the mean for the $75 fine, minus the mean for driver's education. And remember, we're just looking at the absolute difference. We don't really care about positives or negatives at this point. So community service, 1, $75 fine, 4. Oh, we don't need an absolute value there. All right. Community service, 1, driver's education, 1, $75 fine, 4, and driver's education, 1. So, let's make this blue again. This one is greater than Tukey's HSD. This one is greater than Tukey's HSD. So, there is, we can do this a slightly different way, a significant difference with an alpha level of 0.05 between community service and a $75 fine and the $75 fine and driver's education. I'm writing that shorthand. On a quiz, you probably don't want to, but there you go. Okay. We know this one's not significant because 0 is less than 1.945. Now, this is not plain English. In fact, this isn't even scientific because I was lazy. So if I said, what does this suggest in plain English? Remember, these results are extrapolated to the population, so we would say, in the population of traffic offenders, right? We expect that a $75 fine. Now, before I go on, look, these are the only two that are significant, right? $75 fine in community service, $75 fine in driver's ed. So when you're doing plain English explanations, it usually helps to look for what's constant between the groups you're looking at, see what's common, right? So I'm like, okay, $75 fine is significantly different from driver's ed and community service. And then I look at my means. Well, remember, these scores represent the number of traffic citations after the program. And I know that 4 is significantly different from 1 and 1. And I know that 4 means more traffic citations. So in other words, the $75 fine is significantly less effective than driver's education and community service, right? We know that this is significantly different from this and significantly different from this. And just putting it in context, we know that higher numbers mean less effective because more traffic citations. So in the population, we expect the $75 fine is less effective than driver's education and community service for reducing traffic violations. So again, we want to have something that's actionable, right? What do we do with this research? Well, we know that time is more valuable than money, essentially, right? And I'll pay a $75 fine and walk away. But don't you dare make me do driver's ed or community service. That's going to impact my behavior. That's going to make me less likely to have a traffic violation. So the whole goal is reducing traffic violations. All right. So ANOVA is used when you have 2 or more different groups, or in other words, 2 or more different levels of your independent variable. And it's a really powerful tool because with the t-test for independent samples or independent measures, you're restricted to 2 levels of your independent variable. And that really makes it difficult to look at all the questions that you probably want to answer. So ANOVA is awesome for that. And then in the next lecture, you'll see an even more powerful analysis of variance when you can look at 2 different independent variables and how they impact the dependent variable and how they interact to have an impact on the dependent variable.